Okay, in this video I'm going to just go through example problems that are pertaining closer to the high school level. And for the high school level, for inclined planes, the Regents level, we typically don't toss numbers in at all. It's really just free body diagrams and understanding how the components, which forces are going to be canceling each other out, and how we set up our dynamics. So this video, I'm not going to actually throw in any math. The next video will be the next level up, that AP level, in which we will be tossing in some numbers here. Okay, so if you're in the high school level, don't get bogged down by the numbers, because you won't have to. Okay, and so let me just go through a series of examples. Let me write out the first example. Is one that I already gave in the last video, where we have an object just hanging out, just chilling all on its own on this incline, and it is in equilibrium. And so this is going to be what I'm going to reference more often, so I'm going to leave this over here. In this scenario, we do have, I don't know, what color do I want to use as my force vectors in this lesson? I will stick with a baby blue. So we have the gravity, or the gravitational force, is still down. The normal force is perpendicular. And the friction force is going to be opposing the component of gravity parallel to the plane. This is your basic free body diagram for an object at rest on an incline. By the way, I can also have a free body diagram for the same scenario. It would look the exact same, but for an object sliding down an incline at constant velocity. So I'm going to say or, that's not an R there, or constant velocity. So remember, when we have constant velocity, we are in equilibrium still. So the only thing different between this diagram at rest and this diagram being constant velocity is the friction force goes from being static to kinetic. Okay? This is your core. This is what you're going to definitely have to be able to do in the Regents level. You're also going to have to recognize, and this stuff you don't usually draw in if it's a test, but for good scrap work, you do draw it in. You also do need to recognize that Fn must be canceling out Fgy, and Fx, or Ff must be canceling out Fgx. So I'm going to leave that in there. So let's just get through a couple other situations. Like, what happens when we have a situation where we have maybe a car driving up a hill at constant velocity, right? Okay, keyword there, constant velocity. So here we have car driving up incline at constant velocity. We got the weight down. Right? You got that normal force up the plane still. The surface is supporting it. But now we have this car that's driving up the incline at constant velocity. The engine must be doing some work, right? The engine must be pushing up that incline. And we still have friction, right? The car is going to be driving up an incline. So my question is, before I put in the force from the car, what is the direction of the force from, what is the direction of the force of friction? Remember, the force of friction is always opposing the motion. So if the car is going up the incline, shouldn't the force of friction be down the incline? Yeah, it is. We do have an FF here. And before I do my FA, I want to dash in my components. Now think about it. In this scenario, I have two forces that are down this incline. I have the force of friction, and I have the parallel component of gravity. They're both down the incline. If I'm at constant velocity, I need to be in equilibrium in all my dimensions, which means this force that the car is pushing up the incline needs to be quite large. That FA needs to equal both FG and FF. Let's set up my Newton's second law just so you can see what I'm talking about. So in the y dimension, it's still equal to 0, which is equal to the normal force minus the weight. That's parallel, which means the normal force is equal to mg sine theta, or mgy. See what I did there? I changed FG to mg, and I changed the mgy to mg sine theta. I mean, there's nothing wrong with that. I maybe could have written in FG equals mg and mgy equals mg sine theta, but I didn't do that. Okay? You can use this changing up the terminology from Fn to big N. I mean, it's all pretty standard. It's the x dimension that's going to get a little different than what we had before. The x dimension is still in equilibrium, 0, which is equal to now the downward force or forces. Ff is down the incline, and the x component of gravity is down the incline. They're both down the incline. And the thing that would be up the incline is Fa. That means my applied force must equal both Ff plus Fgx. Right? Or I could write it as Ff plus mg. Ooh. This is y. This should have been sine. I'm sorry, y'all. Not sine. This should have been cosine. It's adjacent. This is the one that's sine. Opposite of my angle theta. I screwed that up. This is sine theta. Oops. Again, let's recap what I just did there. Y is the one that's adjacent to theta, so it's cosine. X is the one that's opposite of theta, so that's sine. Okay, so in any event, though, you get the idea here that the applied force is sum of each of those forces. This is probably the most extreme high school level question that you'll be asked to do. I don't think it gets too much more challenging than that. And we can add a few others in here, especially for concept, so I'm gonna. What if we have an object that's trying to fall down this incline so bad, but it's not allowed to because it's tethered down. So object, it's tethered down. So let's draw this here, theta. So we're still in equilibrium, but now we have an object is at rest, suspended on incline. And so we have our weight, Fg. We have a normal force, Fn. We have friction. It's trying to slide down the plane, so friction's still up the plane, but friction's not going to be enough to overcome that x component of gravity. So something else is needed. Normally, Fgx would beat out Ff. This is so much bigger than Ff. So we need one more force up the plane, and that's why it's tethered down. It's strapped to a rope. So we have a tension force in here. It's not that much more difficult. If we set up my dynamics, sigma Fy is still 0, which means normal force minus Fgy is still true, which means my normal force is equal to Fg cos theta, right? It's that x dimension that's going to look a little bit more awkward. It's still 0. It's at rest. It's Fgx, the force down the incline, minus Ff, but now we also have to subtract that tension force. Or another way of thinking about it, let me put it in form of the tension, Tension, I'm going to add this over, is equal to Fgx minus the friction force. So think about this. If the friction force was large enough to equal Fg, so if this was 10 newtons and this was 10 newtons, then the tension would be 0 newtons. But if the friction force was less than Fg, so if this is 10 newtons and this was 5 newtons, that means we need an additional 5 newtons from that rope. This is it for Regents level. Like I said, in the next video, I'm going to toss down the more complex situations dealing with numbers, but I really don't think they get all that much more difficult than this. I hope this helps. Thank you.